honors MSc in Artificial Intelligence from the University of UK. He completed his advanced quantum computing courses from MIT. He received an intermediate certification for an IBM Quantum Challenge Hall 2020. He is a coding school certification in quantum computing organized by IBM. He is involved in global quantum programming workshop from Qword Diploma. He acted as a group leader of quantum machine learning study space for Qword Q Research Study. Currently, he is writing a book on quantum computing with silk programming. He is a technical reviewer for the book Hands on Quantum Information Processing with Python. He is having lot of industrial knowledge in the field of machine learning, artificial intelligence, wireless technologies, signal processing, deep learning. He is having a strong knowledge in PyTorch, TensorFlow, and Python, C++, MATLAB, etc. With this short introduction, I'm handing over the session to our guest, Mr. Suraj.
Thank you so much. I thank KIT for inviting me, and yeah, I'm really thankful to everyone for joining this webinar, and really I'm excited to share my knowledge on quantum computing and the latest developments which are happening. So let us get started. Let me share my screen. Yeah, is my screen visible to everyone? Hello,
Yes,
hello, ma'am.
sir. Yes, sir.
Okay, that's fine. Okay, thank you. So let me start. So you see, this is quintessence of quantum computing and quantum machine learning. So we will know in this webinar, like what is the essence of quantum computing, how it is working, okay, and the recent developments in this field. So just a moment, I think someone is trying to join. Yeah. Okay. So as ma'am has already told about my experience, this is a brief about my experience. I have about like 4 years of experience. It's been now 4 years I'm exploring the field of quantum computing, and it's really fascinating. And almost it's 5 years that I am studying and doing projects on AI and machine learning from my undergraduate days itself. Just recently, I came back from UK after completing my master's in University of Southampton, and it was in artificial intelligence, and it was a nice experience. But yeah, due to COVID, it was not so nice because we were mostly in hostels. We were not able to travel anywhere in the UK. It was a very difficult situation there. So yeah, but yeah, the first semester when I joined last year, it was really nice going to classes, and all the professors have a deep knowledge about their own fields. They used to share their research and everything with us. So yeah, it was a unique experience. And then I completed some courses on quantum from MIT, as ma'am has told, and IBM badge I attained recently, as well as a global workshop on quantum. So currently I'm like leading a group on quantum machine learning, where because this field is a very new field, quantum machine learning. Not many people know about this, and slowly the interest is gaining. So many people are now exploring this field. So recently I became this study group leader at Qworld, and currently I'm writing this book. Almost 5 or 6 chapters have been already completed for this book. There are total 12 chapters and now 6 more to go. And it will be complete by April, and I think they will publish it on May next year. And currently I'm also doing a course on quantum computing where I got selected, and this is conducted by IBM Coding School and Q Cross Q, and it is taught by MIT and Oxford University researchers. So they are sharing their insights on like quantum computing, maths, and the practical aspect. So this is a brief overview of the webinar. So we will start from like why quantum computing, why do we require quantum computing, what is its importance, then we will move on to answer that same question into a more broader sense in applications, okay, where it is useful, how it is useful. We will see what are the basic differences between classical and quantum computing, as well as the properties. What are the properties which makes quantum computing unique than a classical method? We will discuss briefly about the quantum advantage and quantum logic gate. This will be really interesting because I will show you a IBM Qiskit demo. Qiskit is the library with the help of which you do quantum computing stuff. So I will show you the demo in Jupyter Notebook, and then we will go through the overview of machine learning, brief overview. Then we will discuss a bit about quantum machine learning, and I will show you another library called PennyLane from Xanadu. Xanadu is a Canadian company based in Toronto that is very famous for quantum machine learning, and in the end we will have a Q&A. All right. So just one moment. I think somebody is, yeah. Okay. Okay. So why quantum computing? Because you might know that according to Moore's law, the number of transistors doubles every 18 months. So this law was given by Moore, and this Wikipedia image shows you that how the number of transistors on an integrated circuit chip, which is used for classical computing, which are like used in mobile phones, in your laptops, desktop computers, everywhere, how their number is increasing, how they are being miniaturized. When they are more miniaturized, the more number of transistors you can fit in a small package. So this you might have been familiar, but what is happening in the recent years is that we are approaching a limit because we cannot fit now so much of transistors onto the same small chip because of quantum mechanical effects. So a phenomena called quantum tunneling of electrons starts happening where electrons jump across the barrier in the circuits, and because of which the accuracy of that circuit, the accuracy of the classical computing reduces a lot. So because of quantum mechanical effects, we are now moving towards quantum computing, where we will see some progress, and quantum computers will be based on quantum mechanical principles, not on classical principles, because as soon as you go into the miniaturization, quantum mechanics starts to dominate automatically. So next is another reason is prime factorization. So this is actually important for the cybersecurity and cryptographic purpose. Those who have a bit knowledge about cryptography and everything, they know that we use prime factorization. So this is another important stuff why we need quantum computing, because as you know, there are some challenges in cybersecurity. We need to keep our data secure and everything. So because of this, prime factorization of large numbers is required. Even in cryptography also, it is prime factorization of large numbers is required. But like for classical computers, it is beyond the limit. We need quantum computers to do it. And just a minute, like I think somebody is. Okay. Yeah, yeah, I'm really sorry for this because yeah, slowly the students are joining. So yeah, I have to accept them by pausing it in between. So yeah, I apologize for this inconvenience. But yeah, so Yeah, so that is prime factorization. And some of the applications of quantum computing, where applications like where is quantum computing used today, you might ask. So it is in finance. In finance, you do financial modeling, okay, you do asset management, price asset management, you do risk analysis. Like for example, if you want to survive in the finance market, so there are lots of variables, factors involved. So how would you evaluate your chances of surviving in the market? And I can name some banks which are using, for example, Barclays. Barclays Bank is using quantum computing, as well as Deutsche Bank is also using quantum computing. So these are some of the companies, example, who are currently involved in finance and are using quantum computing. Also in quantum in finance, as you see, you do some like experiments, like you do some Monte Carlo simulations, which are just uh, repeated sampling to gain some results, numerical results. So those kinds of analysis and simulations are really helpful with the use of quantum computing, because they are beyond the limit of classical computation. So yeah, just give me one moment. I think many people are trying to find. Next, we have the weather forecasting, because weather is a chaotic system. In a chaotic system, you have lots of variables involved. So in weather modeling, nowadays we are using supercomputers, but even though we use supercomputers, still it is not able to like sometimes predict the weather accurately or change its dynamics accurately. So because of that, it becomes a bit difficult in weather modeling, in forecasting. In that sense, quantum computing can help, since because quantum computing, it is a like a inherently parallel model. You see, like in classical computing, we will see decent differences. Like it is classical computing is sequential, because since you all have studied basic microprocessors, microcontrollers, you know that the computations happen sequentially, but quantum is very different. So if you know about like if you know about like GPUs, graphic processing units, you know that their architecture is completely different. They are kind of parallel. So you can imagine quantum computing to be like a huge, like a massive parallel processing object. So because of that, it can handle many variables simultaneously, not sequentially, but simultaneously, parallelly. And I have already discussed this about cryptography and cybersecurity in the prime factorization fact. So you all know how much this is important, because you might have heard that yeah, many companies are now facing cybersecurity issues, as well as encryption issues. So quantum computing will be a promise in this field. Then another important area is in the simulation of molecules. You see, the simulation of molecules. Molecules are very complex substances, as you know. When you studied in class 10th or 12th about organic chemistry and inorganic chemistry, you know that you drew the structures of molecules. So you know that it's a complex thing. So when you have studied about polymers, in the polymers the hydrocarbons like increase a lot. There are a lot of carbon atoms, lot of hydrogen atoms, okay. And if there are much more complex substances, for example, living organisms have lot of complex molecules which needs to be simulated for medicine and drug development. So for that kind of simulations, we require hugely parallel approach, not a sequential. So it is like totally beyond the like reach of classical computers. It cannot simulate molecules. Even if it can, it is very very slow. But quantum computing holds a promise in this field. And the same thing, the same chemistry is related to material science as well, which will help us to innovate new materials. And finally, we get into AI and machine learning, one of the application of which quantum machine learning we will discuss in brief today. And If you know about AI, you know that it is data hungry. Okay, machine learning, deep learning, all these stuff require a lot of data. So wherever there is a lot of data, we cannot rely on sequential stuff, because sequential means one by one and the computations take a long time. That is why GPUs were built, and that is why GPUs were utilized for deep learning and machine learning. It was because of very this reason, that because GPUs were parallel, and it can process information much more faster than your central processing units, CPUs. So that's why, comparing to that, quantum computing is hugely parallel, much more inherently parallel, I would say. It is inherently parallel. You do not have to build a parallel architecture for quantum computing. It is inherently parallel. So you can take advantage of its parallel nature from the very start. So this table describes the difference between classical and quantum. You see, in classical, we are using classical mechanics principles, like, as you know, in physics, Newton's laws, and all the classical mechanics which you have studied in class 11, 12, and like that. In quantum computing, also, you must have studied basics of quantum mechanics, where you must have studied about the wave nature and the particle nature of electron and everything, de Broglie's principle and all those stuff. Those are all related to quantum mechanics. So quantum computing uses the principles of quantum mechanics to perform computations. Classical computing uses classical bits 0 and 1, and in quantum computing we named it as qubits. Okay, so qubits is two-dimensional. It's a two-dimensional column vector, as I will show you later. And it is like this notation you use. It is called Ket notation. So you have this notation. Inside this you put 0, and inside that you put 1. So once you do this notation, you denote it as a quantum. Then the hardware is composed of CMOS circuits, as you know. That means your normal integrated circuits made up of silicon semiconductor. And here you are using superconducting qubits. Here the hardware is entirely different. For example, I can say you superconducting qubits require a dilution refrigerator. Like, you require a refrigerator to freeze those qubits, so that like, freeze those atoms and nuclei and electrons, so that you can perform computations on them, because their spin actually makes a qubit. An electron spin or a nuclei spin, you have the nuclei particle, they make qubits. So you cannot perform computations onto those small objects until and unless you isolate them from the environment. That is why in superconducting qubits, refrigerators are used, where you freeze them and you isolate them from the environment, and then you can perform computations. But there are some more challenges onto this, which is known as decoherence. Like, in decoherence, what happens is that if your particle, for example, take electron, if your electron is there and if electron starts interacting with the environment, then you lose the quantum mechanical effects. So in that way, you cannot perform quantum computing. Or to perform quantum computing, your electron should be still and isolated from the environment. So that's one of the challenges which researchers are facing today, and they are trying to resolve it. There have been some developments, and researchers are trying to do, like, room temperature quantum computing and stuff like that, like, which you can do in 25 degree or 30 degrees Celsius. But yeah, it will take some more time to develop those, because nowadays, like, if you remember, if you have studied about the classical computing history, they used to be kept in large rooms. The rooms used to be very large in size. Okay, in those rooms, the computers were kept, and the computers were of the size of the rooms. Today, the quantum computing also faces that same thing. There are labs, large rooms where where quantum computers are kept, and they are also the size of the rooms, with lots of refrigeration happening to isolate the qubits from the environment. So yeah, those are the things, and yeah, this one I have already described to you. It's classical is based on CPUs, and quantum is inherently parallel, so it is based on quantum processing units. processing happens in parallel. And next we have is the properties. So as I told you, you can imagine quantum computer to be a very big GPU with some bonus features, with some bonus properties. So these are those bonus properties which you do not have in a classical GPU. So if you can imagine your classical GPU in a quantum counterpart, just you need to add these three properties. These are quantum mechanical properties, and once you add this, then it becomes like a super powerful GPU kind of, you can say super powerful. So what is superposition? So what happens is that in classical, there are two voltage levels, 0 and 1. That means on and off. But in quantum, the case is very different. In this sphere, in this sphere, you can see that there is another state, which is the superposition. Superposition means 0 plus 1 divided by root 2. Why root 2? Because we are normalizing it. Okay. So normalization means you take the coefficients of the 0 and you take the coefficients of 1 and just add them and put it under root. So that is 1 plus 1 under root 2. So you see, we have lots of superposition states in this sphere. So not only this arrow can go opposite also, where the sign will change. Okay, and this arrow can go diagonal as well. So now you can say that it can go everywhere, isn't it? So that means in quantum computing, the qubits can remain simultaneously in this state, like simultaneously superposition state, not only in 0 and 1. They can remain simultaneously in 0, 1, and this. And that is why it is called parallel. Because in parallel computing, things happen simultaneously. So there in quantum, there can be 2 to the power n states, where n is the number of qubits. Here I have taken 0 and 1, so only one qubit. If you have n qubits, then it will be 2 to the power n. So if there are 2 qubits, then there are 4 states simultaneously, all occurring simultaneously. That is how you will perform the parallel computation. And that is the power of quantum computing. Next is the interference. So interference helps you to like measure your superposition state. So if you have this superposition state, so like 1 by root 2 0 plus 1 by root 2. So let me like write some things down. So if you have like this, something like this. So, so you see, if you have like, for example, in mathematical terms, if I say in mathematical terms, your ket 0 is denoted like this, a column vector, and then in 1, ket 1 is denoted like this, like 0, 1. Okay. Using this, you can see that like usually you will see that quantum computing uses a lot of linear algebraic operations, like based on these vectors and matrices and yeah, all these things. So you will see how much the computations are so much easier to do because of these linear algebraic stuff, because of the use of linear algebra. So if 0 is like this, so if I denote a state, which I denoted there, psi, which will be 1 by root 2, and this is a superposition state, of course, normalized. So it has been proved, it has been said that the probability of finding 0, like the probability of 0 is given by the absolute value. Like for example, you can have you can have even complex amplitudes. These are called amplitudes. amplitudes. So these are called amplitudes. You can even have complex amplitudes, not only real values but complex. So then you have to take an absolute value square. That is why in general what we define is like this: alpha and like this. And then we say that prob of 0 is absolute value of alpha square. This is a more general notation. Okay. And prob of 1 is like this. So this is prob of 0, and definitely you can see probability of 1 will also be 1 by root 2 square, which will be equal to this will be half. Okay, so this is the interference principle. Next, let us see the entanglement. So in entanglement is a very like special and it's a, like what Einstein defined it as a like a spooky property, because like what happens is that the pairs or the qubits, they exist together. This can happen like from the like not one qubit. This starts happening from the two qubit stages when both the qubits like occur together, and they occur as a like a single state, and they occur as a single state, and like you can like know the properties of if you know the properties of like one qubit, then you can say the properties of the another, even if they are separated by very large distances. So this is like a image from Scientific American where you can see the particles are there. The particles, these are, for example, you can consider them as like atoms, and they are separated by long, very long distance. Okay, like you can imagine that okay, one particle is on Earth and another particle is on Mars. Even though they are separated by large distances, but still their properties are very correlated with each other. Okay, so for example, let me like show you some calculations on this, because it is really interesting to see like how simple it is using linear algebra to manipulate these things. Okay, somebody. Okay, so let's see. If you see a two qubit state will be like this. It will be like this. Okay, this is a two qubit state. If you can break this, if you can break this two qubit state, then it is not entangled. Okay, but let me give you an example of entangled state. For example, they are called Bell states. So it looks like this. Let me show you one example. So this is a Bell state. Okay, and this state is actually entangled. So what happens is we for multi-qubit systems, we define their operation with a tensor product. Okay, we define their operation using a tensor product. If you want, you can definitely write these things down. These are really interesting stuff. Okay, I really find them very interesting, and how much it becomes like easy to like manipulate these qubits in mathematical sense. In practical, definitely in practical sense, it is really hard, as I told you, because of superconducting qubits and isolation and refrigeration and everything. So if you have like this 0 0, you can write it like this. This is the symbol for tensor product. Okay, now 0 in the previous slide I showed you, it is like this. So you can write it like this: 1 0 tensor product with 1 0. Now what happens is that you do like this. The calculation will happen like this. Then this, then this. Let me write multiplication. So 1 into 1, 1. 1 into 0, 0. 0 into 1, 0. And 0 into 0, 0. Okay. Now you check. Okay, if you consider these elements as A, B, C, and D. So if A, B is equal to B, C, which is happening 1 into 0, 1 into 0, okay, 1 into 0 and 0 into 0, A, B, C, D. If this is true, when this is true, that means that means no entanglement. There is no entanglement in 0 0 state. Okay, but now let us check this whole state. How will we check this? Let us also calculate the 1 1 1 1. Let us also calculate 1 1. Okay, tensor product with 1, get 1. Okay, let me see, somebody is trying to join. Okay, all right. Yeah, so what we will have is like this. Okay, now you can do the calculations yourself, because now you know this is 0 1, 0 1, and then what you will have here is again 0 into 0 0, 0 into 1 0, 1 into 0 0, 1 and 1 is 1. Now for this state you can do like this. Since you now know the values that 0 0 is this, so let us add them. Let us keep the 1 by root 2 outside, and let us just add them 1 0 0 0, and just add them. Okay, so 1 0 0, sorry, this is 0. Okay, so 1 by root 2 will be multiplied here. So what you will get is something like this: 1 by root 2. Okay, and something like this: 1 0 0 1. Okay, now you see again A, B, C, D. You can clearly observe that A, D is not equal to B, C. If you multiply this, here also 1 by root 2, here also 1 by root 2. Okay, 1 by root 2 into 1 by root 2. Okay, so it will be 1 by 2. Then 1 by 2 won't be equal to 0. That means, now this means that it is actually entangled. This is what it means, entangled. So this is in essence like you can, how you can prove that how this thing is entangled. These states, and this state has a special name. This is known as Bell state. So all Bell states, there are several others also like this. So all Bell states are entangled states. Okay, so let us move forward. And I think somebody is, okay, let us Let us go forward. Entanglement. Okay, and this is the quantum advantage. So quantum advantage, what happens is that quantum advantage comes into picture when you can show that there are some there is a problem, there is an algorithm which cannot be solved by a classical computer, but it can be solved by a quantum computer. That is what is called as a quantum advantage. And Google, in October 2019, Google actually showed their Sycamore quantum processor, as you see in this picture. This is taken from Google's AI blog itself. So they published there a nice article. You can also go and give it a read. It's really nice. So this processor, as you see, this processor has 54 qubits. Okay, that means 2 to the power 54 states all simultaneously. Now you can calculate that number. 2 to the power 54 is a very large number. Okay, so and that much states occurring simultaneously. So just imagine the power of quantum computing. In classical, all those states will happen, but you will process them sequentially. But in quantum, 2 to the power 54 states. I don't know like how much large that number is, but yeah, it is a very large number, and all those states are occurring simultaneously, all in superposition. So yeah, so you can just imagine how much power the quantum computing brings. So they showed that they can solve problems which classical computers are not able to solve, and some of them are combinatorial optimization problems. Okay, so for example, those kinds of problems are used in logistics, transportation systems. Okay, so there is one of like a famous problem. If you have heard, it's called traveling salesman problem. So that is a combinatorial optimization problem, and I highly recommend that you give that problem a read. And you can see there, and if you give it a read, and if you type traveling salesman problem and D-Wave is a quantum computing company based in Canada. So D-Wave has used a technology called quantum annealing, which has solved this problem of combinatorial optimization, the traveling salesman problem. So yeah, it's really interesting. I highly recommend that you give it a go. It's really nice. And here comes some interesting parts. These are quantum logic gates. Since you all are from EC computer science triple background, so you all know what are classical logic gates. Okay. So in the demo, I will show you how we will create classical logic gates using quantum logic gates. It's really interesting. I'm going to show you now. And these are just the operation. Okay, so like operations. So let me show you, these are some quantum logic gates. So the Hadamard is used to create equal superposition of qubits. Superposition, as I mentioned earlier. X is like a NOT gate, like a classical NOT gate. It flips the qubit. And these, in the right hand side, you can see their metrics, mathematical notations. These metric notations help you to perform calculations easily. Okay, and Pauli Y is mostly for getting complex phases, complex amplitudes. And Pauli Z is a phase shift gate, it shifts the phase. And in C naught is very similar to XOR gate, classical XOR gate, as you know. That is the C naught gate. Swap means like it will swap the qubits. If the upper one is 0, lower one is 1. If the upper one here it is 0, lower one is 1, then it will swap it. The 1 will go above, the 0 will come down. So like that. This is control Z, that means control phase gate. Control phase shift gate, sorry, phase shift gate. And this is control phase. And this is another important gate, the Foley. So this is also known as CC naught. So yeah, we will see it's really interesting. Like some of the operations I can just show you here. So if you see, if you apply a X gate, if you apply a X gate to qubit 0, then you will get 1. If you apply a X gate to 1, you will get 0. Okay. If you apply a Z gate to 0, then nothing will happen because it's phase shift. So phase shift will only happen when it is like in high energy state. You can say this one is like a high energy state, like spin up state. So like if you have a, like an electron like this, okay, which has a spin, okay, like the up state you can say it as like the zero, and this is like the high energy state as a one, like this, something like this. So when you apply this phase shift to a high energy state like qubit 1, and then you will get it like this. It will add a minus sign. And what about H? That's quite interesting. It creates equal superposition as you told. So what could have happened? Equal superposition, just like this. And in shorthand notation, this is also known as plus state. Plus. And if you do in one, then yeah, only the sign will change. So for qubit 1, and this state in shorthand is usually written as minus. Okay, so these are some basic gate operations. Now mm, let us move on to the interesting part. IBM Qiskit demo. So Qiskit is the quantum computing library developed by IBM, and it was released in like March 2017. And from that time only, IBM has publicly made available a lot of resources for quantum computing, which you can go through. And I highly recommend checking out the IBM Qiskit Summer School, which is available in YouTube. If you type, you will get the full playlist. It's a really interesting set of lectures which you can watch, and it provides a lot of details and knowledge. You can learn a lot. So yeah, let us go into this notebook. Okay, so here you can see quantum logic gates, and we will build a half adder circuits. Okay, half adder circuit you must have studied already in your like digital logic class, digital circuits class. So let us see how it happens. And so this is the library. So from Qiskit, we will import the quantum register. It is like a storage device, quantum register. Then classical register is used for measurement purpose, because you cannot do like a measurement without classical stuff. We perform the quantum operations and measure them on a classical computer. And this is quantum circuit. This will help us to create the quantum circuit. So we import some libraries, and this is for visualization of block sphere. Okay, a block sphere is a 3D representation of qubit. You can say it is a pictorial representation. You will see how it works. So let me start importing them one by one. So yeah, it ran. X gate flips qubits. So what we defined a quantum register. Okay, having a single qubit. You see here you can define the number of qubits. Then we make a quantum circuit, okay, and put this quantum register into that quantum circuit. Then we apply a X operation. Here you can see we apply X gate. You apply the X gate here, and you draw the circuit. So if I run this, you will see this nice diagram. You can see Q0, the qubit is getting all the like qubits are in zero state by default. So if you apply X, then definitely it will go into one. The output will be one. Okay. So if you want to see the output, then the visualization, then we get a nice visualization by running this. You see, this is the block sphere. This is known as a block sphere. Okay, like using a block. bloch, block sphere. So this is a nice visualization. You can see it was in zero state, but since we applied Xgate, it flips into one state. And Hadamard, let's see, creates equal superposition of qubits, as I already mentioned. So quantum register, you create another single qubit. Again, you make a circuit. The same process happens, which happens in this cell. And so so let me run this cell, and you can see H Hadamard gate. Yeah, I am I'm really sorry for this because yeah, as soon as someone comes, I have to like join them in the meeting. So yeah, it's I know it's a little bit strange, but yeah. Okay, so after you apply the Hadamard gate to zero qubit, what happens? It creates equal superposition of qubits. So qubit 0 plus qubit 1 divided by under root 2. Okay, so the same kind of result we will see in the block sphere in 3D visualization like this. You can see. So this is actually the superposition state because 0 and 1, you can see they are on top, and this is pointing in the middle. You can see this arrow pointing in the x direction in the middle, and the middle state is what? Superposition state, as we described mathematically earlier. Here we described it like this. So this is what it is happening. Okay, so yeah, and then let us move on to Z gate, which is the phase shift gate. As I told you, it does anything to the zero qubit. It will only phase shift for the one. So let us see Z. Okay, and if I visualize, you will see that it's still zero. Okay, so this is just a proof that it's zero. And now, okay. So now if I apply a X gate, so here I apply the X gate. Okay, apply a X gate. That means now it is in one, and now in the one you apply the Z gate, so it is like a minus one. So of like a amplitude, like a negative amplitude is being added to the qubit. So then you will get this. Okay, let me run this first. So first X, then Z. So you can see a nice diagram. It shows the visualizations of IBM Qiskit are really nice. You can easily comprehend your quantum circuits. So you can see that it is now flipped towards one. Okay, and the negative sign it won't be able to show, but yeah, it is actually negative. Okay, so let's do Z gate on plus. You know the plus which we created, 0 plus 1 divided by root 2. So H, then Z. So what you will get is like this. Because if you see in the zero state, when you apply Hadamard, okay, then you get this state. Okay, you get this state, and then if you apply Z, so for example this happens like this. Okay, so if you get this state, so if you apply a Z onto plus, okay, let me first let me admit them because these calculations are important. So yeah, so okay, so you see, if you do, then what happens now? How will you do the calculation? So apply the distributive property. So Z on 0 plus Z on 1, okay, divided by root 2. Then what will happen? Z on 0, we know it is already 0. And Z on 1 is minus 1 under root 2. this state and this state is equal, you can see. That means it is minus. So because of this, the phase is shifted in this. You can see the diagram. It is not towards this side, towards x, but opposite of x. Like it's like a minus x-axis direction. Okay. Then C naught gate. So C naught gate. Let me show. C naught gate is usually used to create that bell state, as I told you before. So that bell state 0 0 plus 1 1 under root divided by under root 2. So the C naught gate is actually used to create that entangled state. So let me run this. It is shown like this. Okay, so the upper qubit, the first qubit, the upper qubit is called the control, and this is the target. So it flips the bit. Okay, flips the second qubit. Second qubit means the downward. If first qubit is 1, so only when the first qubit is 1, it will flip that. And now let us move on to CZ gate, that is the control Z gate. So that looks like this. Okay, and CCX, the Toffoli. This is the Toffoli gate. Okay, this is the Toffoli, Toffoli gate. Okay, so it looks like this. You can see the visualizations are pretty neat in IBM Qiskit, and I will definitely share this notebook later after the webinar. You can also like install this library. It's very simple. Pip install Qubit, and you can also experiment and just with these gates. So now comes the interesting part. Now you make a NOT gate. Okay. Okay. So let me just hold on a moment. Let me. Yeah. NOT gate. NOT gate is the X gate. So you can see X operation here. It is applied X. So let us see NOT gate. This is the NOT gate in quantum equivalent. This is how you measure them. This is a measurement. This black color box is the measurement. As I told you, the measurement is made on classical registers, so that's why you needed a classical register, as I imported this classical register. So it is because of that reason. And let us go to AND gate. So AND gate is created like this. Okay, because you see in the Toffoli, if you see the truth table of AND gate and the Toffoli, it is the same thing. Okay, so let me show you, like let me make this a bit smaller. Okay, yeah, many people are joining now. Okay, let me show you. So Toffoli. Okay, so what happens? Like Toffoli is like when both like here also, here also. Okay, so these are all control, and this one is the target. Okay, so when all are one, like all are one, then only if this was 0, then it will come out to be 1. That means the output is 1 1. Okay, but you see, if it is 0, if either one of them is 0, then it will remain 0. So this reminds you of the AND gate, isn't it? Because for AND gate, if you have inputs, then you have outputs, then 0 0, 0 1 1 0 1. Okay, 0 0 0 and 1. So AND gate is 1 only when what happens when both of the qubits are 1. So this is the same as C CX gate. That means the Toffoli. That is why a Toffoli is used to create a AND gate. In a very similar way, you can analyze this for the OR gate as well. So let me show you. So now, what happens is that yeah, OR gate. Okay, so let me run this code. You can see that these two qubits. Okay, so in this operation, let me show you. Okay, this operation is defined like this. Like, if you first, whenever you are trying to make a circuit like this, always like draw the truth table. So for example, input, output. Okay, and this was AND gate. Okay, and this is or just a minute, I'm so sorry. Okay, so yeah, so 0 0. Okay, 0 1 1 0 1 1. So what about OR? For 0 0 it is 0, but for others it is 1 1 1. Okay, because in OR gate, if either one of them is 1, either the bit, then the output is 1. So you can create like how, like for example, here you have it. If you see, let us start if 0 0, the two qubits, okay, and 0 1. That means the input, like these are the these are the inputs. These are the inputs, okay, and this one is the output, for example. So if you apply a CX gate now, okay, just 1 minute. Mm, So if this is 0, if this is 0, then here also 0 will come out. All these are ket. I am ignoring the ket notation, but yeah, please remember that these are all kets, okay, because these are all qubits, okay, not classical. Okay, so I'm just for saving time, I'm just ignoring the notation. So if you see here also, if it is 0, then, and here also for example it is 0, then what will happen, inputs 0 0, here also 0, and this is 0. But if it is 1 here, if it becomes 1 here, then this will flip, it will become 1. So that means 0 0 1. Now you can see 0 0 1. Okay, so are are 0. Okay, and if it is 1, then comes 1. So 0 1 1. So that means these two criteria are fulfilled. You can see by this operation, these two criteria are fulfilled. The next one is, you can see in this diagram in the notebook, next one is this. So how is this fulfilled? This is used to fulfill the next operation, and you can verify it yourself. And when it is 1 0, that means here it is 1. Okay, then it will flip the output. You can see the output is 1, but this is 0. So when it is 0, it will be, what will be, it will be 1. So here also you will get 1. Okay, and for the third operation, you know that 1 1 1, when does 1 1 1 comes? Here you can see in the AND gate. And which gate was responsible? CCX. Very simple. Just apply the CCX for that operation. That's it. Done, and take measurement. That's it. That is how you create a OR gate. So that is the logic, like how you can use the truth table to design your gates. All right, so let's move forward. I think OR gate and XOR gate. Okay, so XOR gate is this one. So in XOR gate, if you see, you do not need that. Okay, so let me open that again. So if you see the truth table of XOR, okay, if you see the truth table of XOR here, okay, let me draw it here. Okay, input. Okay, so 0 0 2 1 1 0 1 1 0 1 1 0. Okay, so you have this. So you see, this is very similar to OR. Only thing is that this is not present. That means what you can say, just remove this, just remove the topoli, and it becomes exorgate, and that is what it is done. You can see, just remove the topoli, and you get the exorgate. So it's very simple. You see, if you just compare the truth tables, you can design these gates very easily. So that is like the strategy to think. And yeah, let me move forward. I think the time is running up. I have to cover a little bit about quantum machine learning as well. So yeah, I hope that you enjoyed that demo. It's really interesting if you like code them. It's really nice. If you see those nice circuit visualizations in front of you, if you measure them and like that. Let us move on to the machine learning. So very quickly, these are some of the applications of machine learning. You can see it is divided into three parts. So very quickly, supervised is when the labels are present. Labels are like teachers, so they guide you. For example, if you have an image of dog, okay, you will have a label associated with it to tell you that yeah, it is the image of dog. And in unsupervised, you will not have the label. So for example, if you have the image of dog, the algorithm has to for example, cluster it. Like for example, identify the patterns and features of the dog to separate it from the cat's images. So that is unsupervised. In supervised, the classification happens with the help of the labels. Okay, so you can consider labels as teachers who are there to tell you the answers, or like a book or something. And reinforcement is very different. It is you are not given any data, rather you are in an environment where you have to learn by yourself. For example, if you have heard about Qubit Deep Minds uh, AlphaGo game and chess game and everything, those games like were created from reinforcement and learning, where those people created an algorithm which learned to play the chess itself. You just embedded the rules of the chess, but after seeing all those rules, the algorithm learned to play by itself. You didn't taught it. Okay, so just 1 minute. All right. Okay, so that is the like brief overview of machine learning. So mainly the goal of machine learning is what, like you want to predict. You have a model. Okay, the model, like all the machine learning is just like based on statistics. Okay, you use statistics to create these algorithms. So this is more like a statistical learning, you can say. So it uses the principles of statistics to make predictions, make future predictions on data, or to classify data. So that is the main fundamental of machine learning. In this here you can see some algorithms. I'm just named some algorithms. Many of you might have been familiar if you have learned machine learning. You know, like regression, linear. It is used for numerical data. You can use decision tree, random forest algorithms as well for making a decision tree regression is there, and random forest regression is also there, neural network regression is also there. So they are used to predict continuous range of values, because numerical values are continuous range, and the classification are categorical. Okay, So in categorical, it is something like, yeah, classifying cats from dogs. So you have the model, you input the image of dogs, and it has to identify whether it is a cat or a dog. So that is the classification. And that is for supervised, and in unsupervised you have clustering, which I give you an example. The cat's images, dog's images will be provided to the algorithm, and it has to figure out itself by the features of cats and dogs, that like how to separate them into clusters. And dimensionality reduction is also the PCA, which is principal component analysis. It helps you to like reduce the dimensionality of data set and identify the most valuable features for which your model like depends on, because your model selects some features. So if you do that for that model beforehand, like if you can identify the most significant features which are going to like make impact on your output, make impact on your prediction or the classification output or regression output, then it is always a good thing to reduce the dimension, because the more dimension you have, the computational complexity also increases, and the computations take a long time to perform. So we keep all these things in mind when we do the machine learning stuff. And all right, so let's move next. So this is like a neural network. Okay, a simple neural network. You might have seen this already many times. The green ones are the input, the deep blue ones are the hidden layer, and the purple one is the output. So you see, in the output you can like it can be a binary classification. Okay, so if I take a simple example for classification only, so the input will be the image of like some dog or cat or something, then the hidden layer will identify the features by itself, and through training, of course, through training, and the output layer will predict what is happening. So you see, weights are associated with the hidden layer. So for example, if I want to like draw this, let me just draw this once. So if you have something like this, if you have like this, for example, these are the inputs, okay, and then you have like hidden layers, okay. So this is this, and like this. So these are input, okay. Mm, and here you have the image, okay, here you have the image, and then you get the output. So let us consider that the output is like a binary, like it predicts 0 for cat and 1 for a dog. So like, yeah, let's assume that this is the classification it makes. It's a binary classification. So inputs is the image, then it identifies features in this hidden layer. Okay, this hidden layer, this is very important, and it identifies automatically. That's the power of neural network. For machine learning algorithms, you need a separate feature extractor. So for let me write this. This is important for ML, for machine learning. You will need feature. Okay, you will need feature extractors, feature extractors. Okay, and for DL, but for DL, deep learning, okay, it's like a black box. Okay, you don't know how the neural network is actually identifying the features. We do not know. There are weights associated. For example, W W1 theta, and for example here also W2 theta. Okay, so they are parameterized by theta. Okay, so theta, what are theta? Theta are parameters. Okay, theta are parameters, and parameters, not only parameter, but specific kind of tunable parameter. Okay, so theta are tunable parameters. That means tunable, or another word, or variational. That means variation means variable, which can change. Okay, which can change. So these are variational parameters, theta, the weights, which can change. Okay, according to the output, it depends on the training. Like a process called back propagation happens, and the network trains itself. So these are variational parameters. So why I'm including this is because this is actually the essence of quantum machine learning. So why these terminologies are important, and that's why I wanted to introduce you to this tunable and variational parameters. This is important. This is the essence of quantum machine learning, as you will see now. Okay, so once you understand this, then rest of the part becomes a bit simpler to understand. So what we have now is that this quantum machine learning, QML. Okay, so they use variational circuits because currently we are dealing with like low level languages as we used to deal, because you all are from ECCSE, so you must have studied assembly language. So you know that for using an assembly language for 8085 microprocessor or 8086, you need to be familiar with the architecture. You need to be familiar with the low level details so that you can code using assembly language. Okay, so yeah, and the same scenario is happening with quantum as well, because yeah, it is very natural to happen, because quantum is in the initial stages. It is not something like where you can write like out of the box, you can build applications or something. Even though many people are now researching and developing quantum software as well, which can run on hardware quantum computers, all those superconducting qubits and photonics based quantum computers. But yeah, for now we have to rely on low level circuit programming until and unless the high level languages are developed, and that is what I am actually writing a book about, the programming language which was mentioned in the beginning uh, of this webinar, Silk, SILQ, Silk language. That is a high level language. It is something like a C, C++. You can say that that language is like a equivalent of C, C++ for quantum computers. As C, C++ are high level languages, they brought revolution into the programming because they used a compiler, and the compiler took care of all the low level circuit details and low level optimization, and like translating the code into like translating the converting the code, your C++ code, to the machine language. So for that only, this Silk programming will act something like that, where you will program your applications easily on a quantum computer, and you do not have to rely on low level circuits. So that is why for QML now, since this is initial stages, we start with variational circuits that depend on tunable variational parameters. So this is important. Tunable. That's why I introduced this terminology. So here you can see 0 qubit is entered through Rx theta 1. Rx is x-axis rotation, simply. Rotation means you need to rotate it through a degree or angle. So theta 1 is the angle. Similarly, after that you apply a y-axis rotation, theta 2, and you take a m. M means measurement. As you know, we already saw, I told you in the notebook also, you saw in the notebook that we do measurements after doing all these quantum computations. So now, theta 1, theta 2 are variational parameters. That means their values can be tuned. And whenever this tuning things comes, then only we can convert this model into something like a classifier or regression kind of model. So what happens is that nowadays we are now concerned about the CQ stuff, the classical data which we have, and we want the quantum computer to solve it. So we want the quantum algorithm to solve it, and that is where our main focus will be for quantum machine learning. Okay, classical data, classical algorithm, that is already there, as you know, in your classical computers. You are solving it, and I do not know much about this case, quantum data and quantum algorithm. I think it is not existing right now, but it might exist well in the future very soon. And quantum data and classical algorithm, yeah. this is done actually, and QML is somewhat like a hybrid. It is like we focus on the QC and CQ part in the quantum machine learning. So yeah. Now let us see. So this is the basic QML architecture. If you have studied the basic basic architecture of a machine learning model, it is very simple. In machine learning model, you do not have like a u of theta, you have like a f of theta, okay, which is your model. So u, why we denote it as u of theta, because all the operations in quantum are unitary, okay. So all the operations in quantum are unitary. Unitary means there should be no non-linearities present. Okay. Unitary means all operations are linear. Unlike classical neural networks where you have to include a non-linear layer, activation functions which acts as a non-linear layer, and you have to include it. So unitary operation, so that brings some challenges because quantum computers are not able to simulate those non-linear stuff because all the operations should be unitary, and this is a like a recommended condition. Like it is an important condition according to I'm sorry, quantum mechanics. According to quantum mechanics principle, the operations should be unitary. So after we apply some unitary operations which are parameterized by theta, that means tunable, which can be changed, we take a measurement, we take the output may be classification or regression, depending upon your choice, then we put it into a cost function. This is important because cost function is that thing which measures your model performance, but it will measure the performance of this thing, this circuit u of theta, this variational circuit. It will measure its performance and check how it is performing. According to the performance, then the answer will go into this update box. It will be updated through an algorithm known as stochastic gradient descent or gradient descent, which you must have heard definitely because it is an optimization algorithm, and it is used for optimizing like minimizing all these theta values to achieve a global minimum or a local minimum where your answer converges and where you have a low value of cost function. You need a low value of cost function. Low value of cost function means very less error. High value of cost function means high error. So you need a low error, so that's why you have to minimize. So that happens through gradient descent algorithms. After it does the optimization, again that theta are fed back. This is a feedback loop that is fed back into this variational circuit u of theta, and this cycle goes on until and unless the thetas converge. Like you get a low cost function. Okay, so very similar now, very this similar the process which I explained now. Let us see this as a demo. Okay, so Xanadu, as I mentioned, a Toronto-based company in Canada, it has introduced a nice quantum machine learning library, PennyLane. I will also show you the website of PennyLane. It's really nice. You can also go and check how they have made so many tutorials available. So let us run this. Okay, so we are doing a simple qubit rotation. We will do this circuit. Let me show you this circuit. Yeah, we will do this circuit here. Program as a program now. So we import PennyLane as QML. We import the NumPy from the PennyLane because that NumPy is actually optimized for quantum machine learning tasks. And let us start running. Then we initialize a device. You can use other devices as well. For example, like you can use IBM Qiskit device as well, and uh, Rigetti Computing as well. Rigetti is also a Canada-based quantum computing company. So let us initialize the device. So this device is like a quantum simulator because we are not running on the quantum hardware, which takes some time to run. So why we are using a simulator. Then what we do, we create a quantum object, and now after creating that object, we make our circuit. So you can see QML RX param 0, so parameter 0, that means theta 1 here, theta 1, same thing in program, theta 1, and params 1 is theta 2, RY, RX, RY. So you can compare. And then we take a expected value for measurement. So let's run. And then we define some parameters and print the output. Like for example, when you since this will do like a flip operation, like Rx and Ry will do a flip operation. Like this is something similar to a X gate, as we learned before, X gate. So you can imagine this circuit to be doing the X gate operation, but the only difference is that it is parameterized by theta. So you are not utilizing the gates directly. You are now using like a parameterized version of the X gate. If we run this, then what is the expected output? We should get 1, right? Yeah, and we get 1 because the state was in 0, 0. The params was in 0, 0. And then we just move, we do a X operation parameterized by theta, Rx, Ry rotations, and then we get a 1. It is like the rotations are happening in this sphere, you know. So let me show you this sphere. So if you have, yeah, if you have this, let me, okay, this one. If you have this as 0, it just, if you see, if you do a rotation along Rx and Ry, and then you will be able to flip it to 1 actually. All those X gates and all the like Hadamard gates and Z gates, those all are actually they are made up of rotations, different rotations. Okay, so I think someone be okay. So yeah, let's move forward. Then we define the cost. So for example, here we define the cost function as we saw in this slide. So consider your u of theta composed of this one, Rx theta 1, Ry theta 2. This is your u of theta. And then what we do, we come here, we have taken the measurement. Okay, we have got the output, and that output is fed into the cost function. So for example, in this case, let us consider the cost function to be our circuit to this. Usually you can take other cost functions as well, but for simplicity purpose, let us consider that the circuit is our cost because we want to optimize the circuit output. So once we define the cost, then we initialize some random parameters, 0.11 and 0.15, and we calculate the cost. We get it as 0.8722, which is quite high, and it is expected because you are nowhere near to 1. You are nowhere near to 1. Okay, let me, there is a diagram. Yeah, you are nowhere near to 1. You are near to 0, 0.11. You are nowhere near to this 1 point something or like 0.99 or something like that. So that's why the cost is high. That means it is erroneous value. 0.8722 is a very high cost. That means it is error. Like it is still near the 0 state. It has not been flipped. Okay. So now for what we will do, we will optimize it using gradient descent. So what it will do is that it will start from these parameters, and then it will take step size of zero point 0.4. So it will take steps to like optimize. And let us run this. Now you see cost after 5 minus 0.41, still it's like a cost after fifth step was still it was a high error. Okay, and cost after 10 it was near to 1. So you can see initially it was here in the 0, but after 10 steps it moved to this, very near to this, like 0.99. You can see 0.99. After 15 step also it was still 0.9999. Okay, so it like moves a bit more closer to qubit 1. After 20 steps still it was like point triple nine triple nine. Okay, and then after 25 steps, okay, you can see that it has converged to 1. So you can see we started from 0.11 because init params is in the parameters. Okay, and you optimize the parameters in this step. So this is the optimization step. Optimization step of parameter. So this is where the optimization step is happening of the parameters where we start in Asia. And you can definitely do, I will share this notebook, do try to change these parameters and see if you change the parameters near to like 1, then what happens. You should reach convergence within a few steps, might be 5, 10, or 15. Within a few steps you will see that it is -1, -1. Okay, and it also showed you the optimized rotation angle. So this is 3.6 into 10 to the power minus 17. That means almost 0. 0.0000, like till it will go till like this point, like -17. And this is 3.14. That means 0 and pi. So yeah, you can see that a zero rotation and a pi rotation. Okay, a zero rotation and a pi rotation you can see along this axis. Okay, a pi means a 180-degree rotation will give you 1, isn't it? If you rotate pi, it's a 180-degree rotation, very simply. So that is what the gradient descent algorithm is actually giving you, so you can verify that yes, the answer is correct. So this was a demo, a small demo for variation circuit, and this is very important concept for variational quantum classifier, which is actually used to like, it is like a quantum algorithm for classifying stuff which you do in classical computing. Okay, so yeah, it's Q&A time, and if you have any questions, please go ahead and ask.
Students, any questions?
Anyone have any questions? You can just ask in the chat box or unmuting yourself. I know that yeah, it's a lot of stuff. I can understand. Okay, these quantum stuff is like these are all like full semester courses in universities and colleges. So yeah, like a lot of content I covered in a very short amount of time. So yeah, it can be a little bit overwhelming. So I can understand. But yeah, if you have any queries, then definitely feel free to ask.
Sir, shall we conclude the session?
Yeah, ma'am, I think students do not have questions, and that is quite understandable because I covered a lot of content in a very short amount of time.
Okay.
So yeah, it can be, it can happen, okay, because it's quite overwhelming. You need a lot of time to like go through all these concepts slowly, slowly. I covered like various things. Uh,
Okay.
so yeah, that's
Can you
natural.
can you just
Mhm.
share us the PPT, sir, so that we can share
Yeah,
it
yeah,
with our.
definitely. I will share you the PPT. Just a minute.
Yeah.
Let
So,
me see.
okay. Sir, on behalf of the management, our Vice Chairperson, Ms. Indu Murugesan, ma'am, Principal
Mhm.
Dr. Mohandas Gandhi, Vice Principal Dr. Ramesh, and Deans, Head of the Department, and our beloved students, we thank you so much for spending your valuable time on sharing your experience and knowledge on quantum computing and machine learning. We once again thank you, Mr. Srinjoy Gangli, for this making this session a wonderful one. Thank you, sir.
Thank you so much, ma'am. And definitely, I look forward to like doing more. And yeah, I really enjoyed. And yeah, and if any student wants to get in touch with me on LinkedIn and everything, so I'm providing my LinkedIn as well. So yeah, I will be happy to connect there. And if you have any doubt, if you have interest in this field, and not only this field, but you can also contact me for machine learning and everything.
Okay. Thank you so much, sir.
Yeah, yeah, you're welcome, ma'am. And yeah, I will be happy to even conduct workshops if students feel necessary, like 2 week
Sure, sir.
workshop,
We are looking
hands-on.
forward to
Yeah,
you.
yeah, definitely. Uh, this is my LinkedIn. So I have shared my LinkedIn and I have shared the slides as well. So I will share the notebooks, ma'am.
Okay.
Uh, yeah, I will share the notebooks with you, and
Okay.
then you can share those Jupyter notebooks with students. And yeah, if they want to experiment with these things more, so yeah, they can just make different things using quantum circuits if they are if they have the interest to do this.
Sure, sir.
So
Sure.
yeah, I will share this after the webinar.
Yes, yes.
So
Thank you, sir.
yeah, thank you. Yeah, thank you so much everyone
Yes.
for joining. Thank you, ma'am.